At 12:15 for lunch. That gives us a while, 4 to 5 minutes plus questions. So our speaker is Milan Maksimovic from Observatoire Paris, and the title of the talk is Solar Wind Electrons, Basic Observations in Basic Physics.
Okay, so good morning. Does it work? Okay, so here is the outline of my talk. I'll first show you briefly some observations in the solar wind, focusing on the solar wind electrons. That was also first of all, I'm sorry, I would like to thank the organizer for the invitation. It's a very nice place. So I was asked to speak about solar wind electrons. So I will start with basic observation of solar wind electrons. Very briefly, how do we measure them? I'll say then a few words about the radial evolutions of the basic parameters and some basic physics, including only basically Liouville and then collisions. Forgetting completely about particle wave interaction. I will leave that to Justin and Stuart for tomorrow. And so I will then there present some exospheric models, some kinetic simulations that were made by people in order to try to understand the shape of the distributions that we observe and its radial evolution. And then I will give some conclusions. So as I said, I will not speak about turbulence, but anyway, I will, however, start with a slide to answer a comment by Tim yesterday during his very nice talk about some work on the electron scale. So this is a turbulence spectrum observed with the cluster instruments. So this is the proton range. This is the electron range that Tim was speaking about. So this is the results from Alexandrova et al., which was published some time ago, 1 year ago, and it has been a subject of some debates among people who are working on that topic. But however, what I wanted just to show from an experimentalist point of view is that here, what we see on the electrons, there has been a debate to know if this break here, or if the slope could be fitted by some exponentials or whatever. If we see dissipation, actually, I mean, what we see is not directly dissipation. What we see is a break on the slope, and I think that this break occurs at frequencies where the signal that we observe is 2 orders of magnitude larger than the search coil sensitivity. So I think that from this point of view, only from the data point of view, I'm not speaking about the interpretation, I think that there is an interesting result in this study. I mean, there is clearly a break. I think that we might in the future see with the next projects with the better sensitivity and also going closer to the sun, with having the turbulence spectrum increasing, we may see this better. But I think that there is evidence here for another break at the electron scales.
I have a question about this, Claude. So this is the frequency spectrum measured by satellite as the solar wind blows past it.
It's exactly the same as Tim explained. This is measured in the waveform domain. You have a magnetometer, then a search coil, so you waveform, and this is measured in the spectral domain. But it's basically exactly the same.
So there's a point on here for the ion cyclotron frequency, but if I go to the frame moving with the plasma, that would. I don't know how to relate this.
How to relate the
Doppler shifted ion frequency would be somewhere else, not there.
Oh, these are average values that are obtained during a time interval, and I assume that this is.
He's saying these frequencies are the wave numbers or the frequencies.
These are frequencies.
Well, yeah, I think the things that have lambdas on them are probably wave numbers. F lambda I is probably the convected ion inertial length, and F rho I is probably the ion gyro, assuming that there's no Doppler shift. If you don't know, without knowing what K is, you have to assume one or the other.
So these are special, and these are.
Lorenzo wants to say something.
What's FCI? Just say that maybe the
I'm
where
sorry,
the
FCI.
real
That's
gyro frequency is, it can be inferred by where the change in the slope is. which is a little bit on the right than the theoretical. No?
Sorry, FCI is this probably the cyclotron frequency.
But
Rho I
it's
is
the cyclotron frequency
gyroscale.
of the signal that satellite
Okay, I
is
get it.
picking up,
Yeah.
and that's dominated by KV solar wind.
Right. So
Right?
presumably in the plasma frame, this is all well below cyclotron frequencies. That's still the point of view?
I
or-
believe that, yes. That's
Okay.
contentious, but I think that's the case.
Okay.
It's all well below the gyro frequency, so that's all just K rho. So you could write K rho on the line, but
Anyway, I assume maybe you will talk more about that
I
tomorrow.
can talk a little bit more.
Okay. Okay, so now coming back to the electrons and to the particle observations. So just very briefly to put the scene, this is the solar wind as seen from the ecliptic by the Helios spacecraft. So this is the time going on, the density, the speed. So basically the solar wind, as Tim said, it's a combination of slow and fast wind. The slow wind is coming from the equatorial regions of the sun. This is an X-ray image from Yoko, where the temperature is between 1 and 2 million Kelvin. The fast wind is coming from the coronal holes, where the temperature is lower. And here you have the basic properties. I mean, Tim gave some of them. It's mainly ionized hydrogen. There are some heavy ions that we also measure. Here is the bulk speed of the slow wind, the density, the pressure. You see that the temperature here, the dynamic pressure here, the temperature of the electrons and protons are more or less the same, which gives large, as Tim said, large thermal speed. The electrons are subsonic, the protons are supersonic, and the typical energies here are given for the electrons and the protons, and this is the energy coming from the bulk speed. For the fast wind, which is a bit faster, and actually which is a little bit more puzzling than the slow wind in terms of the thermodynamics itself. These are the typical bulk speed values and the temperature. So usually we say that in the solar wind, the protons, they transport the momentum, they determine the viscosity. The electrons, they transport the heat and determine the conductivity. So how to measure distribution functions in the solar? So you have a spacecraft, and the big difference, of course, is that we have a spacecraft and an analyzer which is much smaller than the characteristic scales in the medium. So we have a test point particle, and on this spacecraft we put analyzers, which are given here, and basically what you do, you count the electrons. And the velocity or the energy selection is set by the entrance of the potential. I mean, if you change the potential entrance of the grid, then you can select the energies. You repeal some particles with lower energies. So the energy selection is done by that, and the look direction is set by the geometry of the instrument or by the fact that the spacecraft is spinning. So we usually use the spinning of the spacecraft, and because the typical spin rates are of the order of seconds, and because also of the count rate, it's very difficult to measure in the solar wind. It's easy to measure distribution function, but it's very difficult to measure them on very, very short time scales, on time scales that would be needed for looking at the dissipation of energy in the turbulence. So, I mean, this can be done, but up to now it has not been done, and there are plans maybe to do that. There is just a little problem with the spacecraft charging effect in order to be complete. So the spacecraft is in the solar wind. It's illuminated by UV, so it's emitting photoelectrons, and it's collecting solar wind electrons, and the balance between these two currents determines the spacecraft potential equilibrium, which is typically of the order of 2 to 10 volts. So if you remember the numbers, for the protons this is absolutely not a problem because they are keV, but for the electrons you have to, if you want to measure correctly the distribution function, and especially distribution functions, I mean in the core part, in the low energy part, if you want, for instance, to measure drifts, velocity drifts or currents from the distribution functions, then you have to carefully correct that, and this is not an easy task, but it can be done. Okay, so if you put such an instrument in the solar wind, you always observe these kind of distributions. So this is perpendicular to the magnetic field. So we measure also the magnetic field locally. So at each measurement we have the local magnetic field, and we measure parallel and perpendicular to it. So this is perpendicular to the magnetic field. This is a Ulysses distribution function. The squares are the data, and blue lines are some fits. So what you see, and this is in a log scale. So you see that there is a Maxwellian core, which is here in red, which is about 95% of the density. And there is always an isotropic halo here, which represents more or less the remaining 5%. And this isotropic halo is always present. It's present in the perpendicular direction, and it can be fitted. I mean, there have been several papers on models for fitting this distribution, but the best model, I mean, and this is just empirical from an analytical point of view. I mean, you just feed the data with no physics there, is a Maxwellian for the core, actually a B Maxwellian with the temperature and isotropy, and the B Lorentzian. These Lorentzian or kappa function, which are actually power laws, I mean, where the flux decreases as a power law as a function of the speed with a given power law kappa here.
Just a point of clarification. When you refer to bi-Maxwellian or bi-Lorentzian, you're distinguishing between the parallel and the perpendicular, and that's the anisotropic.
Exactly.
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 So we always assume, almost always, gyrotropic distribution.
And actually, we can assume that and measure that. I mean, and they are. Okay.
Unless
There are
it's
sometimes.
shock, it's just
Okay.
nice.
There are sometimes. Yeah. There is a discrepancy which I also. Okay. So this was in the perpendicular direction, and as I said, you can spin the spacecraft and you can look at different loop directions. And here is a plane which is the V perpendicular, V parallel plane, and you have this is an observation now on the Helios spacecraft, which was launched in the 70s, and where you had 8 sectors actually in the angular directions. And what you see, and here are all the 1, 2, 3, 4 cuts. So parallel, perpendicular, and in the direction which is 45 degrees. So what you see here, this is the perpendicular cut. So this is kind of this one. In the parallel direction, you have in the anti-sunward direction, the blue here, you have an excess of electrons by something which is about 2 orders of magnitude in the flux of electrons here, and this excess actually occurs in this direction and also in this direction. So you have a beam or a strahl, which has a typical density which is comparable to the halo one, but which is a collimated population. So you have actually 3 components: a core, a thermal core, a halo which is isotropic, and you have a strahl which is along the magnetic field line. And what I try to show you is that basically we understand the physics which explain the shape of this distribution function and its radial evolution, but still, of course, problems are remaining. I'll say just rapidly a few words about protons, but I assume Justin will say more. The protons are basically, and the protons are supersonic, so they are not centered the plasma frame. They are moving at the bulk speed. The protons are B-Maxwellian. B-Maxwellian, I mean there is a temperature and isotropy. And there is a beam that you can see here, which is often observed. It's not 100% of the time. The beam is related to the drift. Speed of the beam is related to probably to the Alven speed here. There is also a beam which in some of the instruments that measure the protons which are due to the helium, and you have sometimes to make the differentiation between the proton beam and the helium, which is not always easy. And if you look at the temperature anisotropy and its evolution with the Helios spacecraft, so the Helios spacecraft made observation from 0.3 AU astronomical unit to 1 AU. And this is the magnetic moment, and what you see is that clearly the magnetic moment is not conserved. And you have clearly wave-particle interactions, and you have additional heating, and I'll come back to that later. Also, just a slide on the heavy ions, but also maybe on the helium. Justin, you will say something. So these are the heavy ions. The heavy ions are more complicated because the flux is much slower. You have to wait for more time to collect sufficiently particles to produce a distribution function. But what you see here is that basically there is, compared to the speed of the solar wind, there is always a shift, which is of the order, again, of the advent speed. And also another property of the ions is that the temperature compared to the protons is mass proportional, more or less. And also, as for the electrons, if you look at very high speeds, you have a departure from Maxwellian. These are just observations. So just to say a few words about collisions, of course we all know that the cross-section here can be obtained by equalizing actually the kinetic energy and the potential energy when two particles come close together. From that you have the expression of the cross-section, and from that you have the fact that the free path in the particles actually is a power is a function of the speed to the power 4. So when we say that, I heard yesterday, I mean, collisions are local, Coulomb collisions are local. This is probably true when you have, for instance, in the chromosphere, where you compare, if you compare the mean free path over the density scale height, the Knudsen number in the chromosphere, it's very small, 10 to the minus 13. So this is probably the case. But in the solar wind, it's of the order of 1. So clearly in the solar wind, the mean free path is not local. The Coulomb collisions are local probably for the isotropic core. You see here, as was said by Tim yesterday, the typical mean free path for the core are the order of 1 astronomical unit. You have several collisions, and this is probably sufficient to keep a Maxwellian core. But for the halo here, just apply this V4. You see that in the range that we observe, we have particles here, electrons, which can come. I'm speaking only about collisions, nothing else, of course. Of course, there are waves which maintain the locality. But from the collisional point of view, these electrons can come from very far from the region where you are measuring them. So collisions are not local. And we know that the solar wind obeys basically to the continuity equations, and the locality which is given there is the turbulence or the instabilities, but not the collisions. Okay, radial evolutions.
Sorry, could I just ask, so how many sequences does the tail start?
Or here, the breakpoint energy here is basically
Like 3 orders
something like oh yeah, 3 orders. Yeah, the density. This is a log scale again.
Yeah.
So this is only 5% of the. So it's not a lot, but it can have some effects. I will show that later. But typically, the energy here is a few times the temperature of the core.
So it's
A couple of thermal energies.
It's a couple. If you do a square of time, it's a couple of thermal energies. So radial evolution. So here you combine Helios and Ulysses observations. So Ulysses, which observed up to 3 astronomical units. So I guess this should be in the fast wind, I don't know, but more or less the results are not very, very different. As if you remember the first slide, the electrons, they behave more or less the same in the fast and slow wind. The strahl is maybe more important in the fast wind. The protons are hotter in the fast wind than in the slow wind. But basically, what you observe, so this is the density, and you see it's varying like R-2. So this is really a time stationary, we assume that it's a time stationary solar wind. And for the temperature, it's like R-0.6. And the error bars here are not put, but I mean they are within, something like 0.1, 0.2. So what you see is that the temperature is in between an isothermal expansion and an adiabatic one. So in the case of isotropic, not CGL, just purely isotropic, the adiabatic temperature would vary like R-4/3. And what we see is that the electrons obey a radial variation for the temperature, which is in between adiabatic and isothermal. So, and for the protons are a little bit more closer to the adiabatic, but still there is an extra heating which is needed for both electrons and protons to explain the temperature gradient. And here the temperature, so this is the core of the temperature, but you can also compute from the distribution function the temperature as being the second order moment of the distribution, whatever it is. And also this temperature, including the strahl and the halo, also is not varying adiabatically.
Quick question. So you're talking about adiabatic expansion is the primary thought, but you have this electron transport that seems to be very, no collisions. Is there any losses because of just rapid transport, along the line rather than just the expansion?
Actually, that's what we want to determine. I mean, what's the transport energy equation, actually the precise one in such a medium.
Right. So it could be that you need a lot of heating because you have additional losses and from other mechanisms, not just expansion. Is that possible?
Possibility, but when you speak about losses, in which term losses?
Well, I'm thinking in terms of
Not
leaving the
radiation.
system in a parallel sense, and maybe this isn't appropriate for this system, but you're considering this finite size box where you're considering energy transport in, and you have expansion, but you also have this electron connection out of the system. I don't know what that means, where it's connecting to, but certainly thinking about in terms of laboratory experiments, if you have a situation.
You're speaking about the board.
Parallel losses, right? Yeah.
It's not heat. You're not speaking about heat conduction.
Well, it could mean it's whatever process.
Yeah, the heat conduction. Yeah, I will say a few words. I mean, we don't know what's the heat conduction in precisely in such a medium.
Right. Okay.
It can be very funny.
Sure. I don't doubt that.
I'll show some.
Just a short question. I mean, the same figure we saw yesterday, it was rather the mirror instability, which was not.
Oh, this was for the protons. This was for the protons. This is electrons. Again, I will not speak about that. This will be done by Stuart and Justin. But just to show you that there are evidences for both collisions and instability shaping the electron velocity distribution and mainly the core of it. So this is some work which was done recently by Stverak et al. So here you have the beta of the plasma, the anisotropy, and this was shown yesterday. You have, so this is something like several years of data. So here you have something like 95% of the data are here. But at the border, when really you are large anisotropies, this seems to be bounded by either Wheeler or Fyrose instabilities in the case of electrons. And Justin will show much more about the protons for that. And also the collision age here. If you put the collision age, which is you have the expansion speed, the distance, and the collision frequency. You define it like that. So you have three different collisional ages, less than 20, between 20 and 60, and more than 60. And you see that the trend here, again, the beta and the anisotropy, the more you are collisional here, the more you tend, for the core, this is again for the core, you tend to be isotropic. So clearly, collisions play a role, and when you are really, for large anisotropies, the instabilities play a role. Okay, so now radial evolution of the distribution function. So this was a work done recently, where actually we fitted the core with the bi-Maxwellian, as I said, the halo with the B kappa, and we fitted for the first time, and this was not done up to now, the kappa, the Strahl distribution function with an analytical formula, which is here actually a B kappa distribution again, with the flat top, which is actually it's a beam. So, and you can see here the result of the fitting. So the stars are the observations. Okay, the dashed line that you have here is the core. The dotted dashed line, this one here and this one here, is the halo. And in addition to the halo, you have the Strahl. So the Strahl is the dotted line here. And this is in the parallel direction, and in the perpendicular direction, you see that the Strahl completely disappears. As I said, the Strahl is only in the radial direction. So you only have the core, the dashed line, and the halo, the dot dashed line, which is here. So this is a purely, it's a purely empirical model again, with no physics there. But it is interesting to really measure, to quantify really accurately for the first time the various densities, the various components between the core, the halo, and the Strahl. And the way also we define the halo and the thermal and the non-thermal part is that because of this truncature with flat top distribution, we cut in the inward, in the lower speed range, the halo. So really the thermal is the black part here, and the non-thermal are really the wings. We do not take into account for the non-thermal part some electrons that could be that could be in the core energy regime. So if you do that, and if you plot the radial evolution, so this is a function of the distance from the sun, of the relative density. So you put the relative density, the density of one population divided by the total. So this is the density of the core population divided by the total. The stars here is the density, the relative density of the halo plus the strahl divided by the total. And you can see that this relative density is about 6 to 7%. And here, this is a new result which shows that the relative density of the halo, which are the stars, the diamonds here, compared to the relative density of the strahl, is anti-correlated. Actually, when you at 1 IU, and we used to have, this observation at 1 IU, they are more or less the same. And they remain more or less the same this is in the Ulysses radial range. But as you go closer to the sun, most of the non-thermal electrons, so these are the non-thermal electrons, these are the core electrons, these are the non-thermal. Most of the non-thermal electrons are in the strahl population. And there is no more halo as you go closer. So it seems really that the strahl is transformed into the halo with distance, probably by particle wave interaction, by turbulence, there have been actually in the literature several, and I have a list, I can give you that, several theoretical work in order to explain this kappa distribution function in the solar wind. There have been work on non-extensive entropy, work by Lubner, Salis, and there have been, just Stuart sent me a few minutes ago, some work about the equilibrium between the thermal noise, the electromagnetic, the electric thermal noise that you get in the plasma because of the motion of the electrons. So an equilibrium between the the thermal noise and the distribution function, which actually could yield a kappa distribution function in a natural kappa distribution. So there have been some work to explain from, not based on observation and fitting, but based on some physical inputs, the existence of this distribution. But still, it seems from the observations that there is an evolution in that. We have a given state at 1 IU, but as we go closer to the sun, we have more strahl electrons than halo. And if we extrapolate that back to the sun, so these are observations in the Helios. So now this is in solar radii, 200 solar radii. These are observations in the Helios radial range. But as you go closer to the sun, and this is at 10 solar radii, and this is just, again, an empirical extrapolation of the fitting parameters, and you have something like 15 fitting parameters to fit all the distribution functions, all the measurements. And you have, of course, much more. If you look at the energies and the radial and the loop directions, you have much more bins than fitting parameters. So if you take all the fitting parameters and you extrapolate back to the sun, you obtain a distribution which is something like the red one, where you see that, and this is the core. So you have basically a core with only a strahl which is here expanding in the anti-sunward direction. And this is basically more or less understood from only collisions and the effect of a non-polar electric field that I will speak about right now. So, if you forget about waves, you just take particles and just first principles, you look at the sun gravity and you look at the temperature in the corona. So the electrons are the gravitational energy is much slower than the kinetic energy. So for the electrons, what happens is that they escape easily from the corona. For the protons, it's the opposite. They are bounded because of the mass, by their mass and by the gravitational energy close to it's not the case as you go further, but close to the corona, to the sun, is larger than the kinetic energy. So the protons tend to come back, and then you have a deposition of protons, and then you have an electric field. So you have an outward electric field, which is setting in the plasma in order to repel the protons. And in all the models that you do, either purely collisionless exospheric models, or in collisional model where you add some collisions, you have to the main unknown is this electric field. You have to solve that for the electric field, and basically what we do, we impose quasi-neutrality, or solving the Poisson equation remains to that, and we can solve that by step at all the altitude from the sun in order to get this electric field, and then we have the evolution of the distribution functions. So in this approach, the wind is accelerated. I mean, there have been several in the history of the solar wind models. There have been thermal pressure models. There have been wave pressure models. There have been models at the beginning electron-driven, which were the thermally driven models. Then proton-driven. In this approach, the wind is accelerated mainly because of the electrons, and it's electron-driven, but because of the electric field. Okay, and if you do more properly, if you solve more properly this problem, you can do it just by solving the Liouville theorem in the exosphere. So these models are basically, this is the Jeans escape of a planetary atmosphere, where you look at the function, you have a distribution function, you look at the particles which have a speed larger than the escape speed, and you throw your particles and you compute the fluxes. So this is the Jeans escape in the case of either the Earth. I mean, this was applied also to the wind coming from the polar wind from the ionosphere, and also from the solar wind. So you solve Liouville. You have different kind of particles. You have particles that escape, particles that don't have enough energy and come back. You can have incoming particles in the case of the Earth, but you remove that for the case of the solar wind because you assume no boundary. And then you have trapped particles. And these trapped particles, and what you do for each of them, you basically solve Liouville, and the moments of the distribution function at any distance here in the exosphere are a function of the electric field. Actually, you know the gravity, but the electric field. And there has been a dilemma for the trapped electrons. Actually, if you do these models properly, so the trapped electrons here, in principle, if you have no collisions, you cannot fill these populations.
So you prescribe the magnetic field and you solve for the electric field, is that right?
No, we assume a magnetic field, and we assume magnetic moment conservation.
And you solve for the electric field.
And we only solve for the electric field. The only unknown is the electric field. And actually this is similar also, I mean the problem is the same as the one of the spacecraft charging body. And also you have these problems of the trapped particles also for spacecraft charging bodies, where there is always this dilemma, these trajectories. In principle, if you have absolutely no collisions, you have no chances to fill them, because what you set is the distribution function here at the exobase. So you need, in order to fill these parts, you will need them to be here at the exobase. But if these trapped particles come to the exobase, they become escaping particles. So there has always been this dilemma, and usually people, they put a distribution function and they assume a continuity. But physically, if you think about that, if filling this region is equivalent to assuming a minimum amount of collisions in order to have a wind. And I'll come back to that later when we compare with some kinetic simulations. Okay, so if you do that, and because I said that the electrons actually are pulling the wind, you can have an effect depending on the distribution function that you put in the corona. So if you do that, and if you solve correctly for the electric field with the Maxwellian distribution function, you obtain something like a 400 kilometers per second wind. You have a given interplanetary electric field, and you accelerate the wind up to 400 kilometers per second, basically given the temperature and the distribution function. But if you assume non-thermal distribution function, and for instance this kappa function that we have used, so now we take kappa function, we observe them in the solar wind. There is an evolution of that in the solar wind, but if ever we assume that they exist already in the corona, then what's happening with the kappa function? So this is, you see the different kappa function, this is a Maxwellian. When kappa tends to infinity, you have a Maxwellian. So this is a kappa of 10, 4, 2. So as the kappa is decreasing, you have an increase of the non-thermal part. And if you set here an escape speed, basically what you say is that by decreasing the kappa here, or increasing the number of electrons, of suprathermal electrons, and even if the number is very small, a few percent will suffice, you increase the flux of electrons, and then you increase the electric field, and you increase the bulk speed. So in these models, here you have some different bulk speed as a function of distance for different kappa models. So kappa equals 6 is close to Maxwellian. So you have typical 200-300 km per second winds, but you can explain the fast wind with these models if you assume really important non-thermal tails. And the drawback of that is that you have an important heating, and maybe I'll say a few words about that. This distribution function, because you have non-thermal tails, what's happening is that there is a kind of velocity filtration effect where only you have an electric field, so only the more energetic particles can escape, and if you have a lot of non-thermal particles, then you increase the temperature drastically in the low corona. They have been, so now I'll compare with some kinetic simulations which have been done, either purely particle simulations here by Landi and Pantalini, and also Lorenzo has worked on that recently, or analytically just by solving here the Fokker-Planck equation here with a Coulomb, an appropriate Coulomb collision operator. This was done by several people. And you will see that the results by these two approaches are very similar. So if you, again, you just assume now you add collisions to your particles. So here the way you add collisions is by increasing the number of particles that you have. So this is a 1D model. It's 1D in space and 3D in velocity. And what you say is that when you have two particles, and the particles can move in the gravity and in the electric field, and when two particles come close together, then you can have a collision operator with a Coulombian cross section, and you can mimic like that Coulomb collisions. So if you do that, this is the result that you obtain. And interestingly, what you see, these different curves show you, as a function of the distance, the speed that you get, and this is the Mach number. So here, after 1, of course, you get a supersonic solar wind. But what you see here, this is with an increasing number of particles. So this is with an increasing number of collisions. So the interesting point is these models, if you take these very simple models and you assume absolutely no collisions, and so these are kinetic simulations, purely simulations, you assume no collisions, you have no wind. So you need a minimum amount of collision in the solar wind to produce a supersonic wind. And this is actually, this solves the dilemma of the trapped region, where in order to fill the trapped region, you need a minimum amount with a purely completely different approach. I mean, you need a minimum amount of collisions to produce a wind, to find a solution for the electric field. You obtain exactly the same if you, from a completely different approach.
What is that minimum amount? What does it correspond to? Collisional height?
That's a good question. I mean,
is it the collisional height?
A given Knudsen number. I mean, what you increase the Knudsen number in the system, so the minimum amount which, and there should be
so it's a collisional scale.
Yeah,
it's actually that drives it.
This is the Mach number relative to the ion sound speed?
or something like that. Yes.
Something like that, not the Alfvén speed.
No. This is the Mach number of the sound speed. Yes. Yeah. In the simulation. Yeah.
You don't think it's faster?
No. This is this simulation is the
It's not negative.
there is no magnetic field in this simulation. They are very simple. I mean, just an electric field, the particles, and the gravity. And now, if you plot the distribution functions that you get in these models, so this is the distribution function in the parallel direction, normalized with some speed. So this is at the base. So at the base, if you put in this simulation, you can put a Maxwellian. So if you put a Maxwellian, so this is the dashed line is I think at the beginning of the simulation, and the final one is at the end of the simulation. What you obtain here at 45 solar radii actually, if you look here at the speed, so this is 0, so -2, +2, and this is +4, you obtain actually a strahl. And you obtain a strahl at a speed here in the anti-sunward direction. So you obtain kind of truncature of the distribution function in the anti-sunward direction, which is simply related to the electric field, the local electric field. So, I mean, this is the escape speed of electrons. The gravity is negligible, so this is the escape speed of electrons. And only electrons with a larger speed than this one, they can escape, and they never come back, because you have only collisions play a role here in the core domain, and the particles with a large speed, they don't collide enough to come back. So basically what you, in these simulations and in the exospheric approach, what you say is that the core and strahl components in the solar wind can be explained only by simple principles, which are collisions and an ambipolar electric field. And for the strahl, it's more complicated. Then there has been also some extensive comparison between exospheric models and this kinetic simulation, but at various parameters. And actually here, this is plotted as a function of the thermal energy divided by the gravitational energy. So this is basically R0 KT0. This is the coronal temperature divided by the gravity. So the solar wind and the solar corona is here, but this is extended over a large amount of these parameters. And here you have the normalized thermal speed. So the stars here and these diamonds and triangles are obtained from, okay, so these are some previous models. The stars here, and here are simulations. And what you can see is that the general trend here, when you compare the simulations here, the stars, and the models which are in the full lines here with Maxwellian distribution function and here with kappa, there is a general trend in a good comparison between these two models. And there are two branches of solutions. With the Maxwellian solution, you have an increasing normalized thermal speed as a function of this ratio between the thermal and gravitational energy. And with models with kappa functions, actually you have the opposite. You have a decreasing trend as a function of these parameters. And this seems to be quite universal. So now what happens, there have been other works, and again by Filippo Pantalini and Simone Landi, about the heat flux. What's happening for the heat flux, the energy transport in the corona, for instance, if you assume these non-thermal distributions. So in this simulation, this is again a particle simulation as the one that I explained to you. You have, so this is basically mimicking the transition region in the corona. So you have a given temperature T0, which is lower than the temperature at a higher altitude. And in your model, you keep the temperature constant here and here. That's the only thing that they impose in their simulation. And if they have a Maxwellian distribution function, then they can compute, actually they can numerically compute the heat flux. You just look at you compute the heat flux as the third order moment between particles which go in this direction and particles which go in that direction with their given energy. And the heat flux that they obtain here, that you would obtain if you have a Maxwellian here distribution function, will of course go from the hot to the cold side. But if you add non-thermal part, and this is observed both in simulation and in analytical solution, what you have is that you have the heat flux, you have a net heat flux going from the cold to the hot region. So the heat flux changes direction if you assume, and here the temperature again is the total temperature of the full distribution function. is the second order movement. So the heat flux goes in the wrong direction. And so again, these are the simulations, and this is a model. This is solving the Fokker-Planck equation. So this is as a function of the parameter kappa. So here, no large non-thermal tails, here closer to a Maxwellian. So here this is 0, and what you see clearly is that for values of kappa of the order of 6 to 10, which is more or less Maxwellian, and this is comparable also in the analytical solution, you have the heat flux which is negative, which is going in the direction of in the right direction. But when you decrease the kappa, you increase the number of particles, but still keeping the temperature. This is the important point. Then the heat flux goes in the other direction. And here you obtain the same with this simulation. Okay, so it's time for conclusions. So non-Maxwellian electron distribution functions are always present in the solar wind. I mean, for the electrons, we always see them at least even up to 0.3 AU. The core Strahl structure seems to be more or less understood. It results from natural expansion in an ambipolar electrostatic interplanetary field, and only Coulomb collisions. So the collisions are enough to maintain the core part of the electrons Maxwellian. Of course, there is an anisotropy. This anisotropy is controlled both by the collisions but also by instabilities. But for the halo part, it seems first that the halo comes from the scattered electrons from the Strahl, and this develops as you go further from the sun. And now what needs to be understood, in addition to the, of course, to the additional heating processes, is the way exactly the halo is formed. Does it only result from the Strahl, or do you have also close in the corona a non-thermal population which is important there? That is an open question. And then, of course, with these heating processes, which are additional heating processes which are needed, the main point is that for the solar wind, we still don't have fully comprehensive equations for the transport of the energy in this medium. And for instance, one of the reasons may be that because the collisionality for the electrons, they can come from everywhere in the interplanetary medium. And as a conclusion, I think that we need to go closer to the sun to make measurements there. That's the main conclusion. Okay, thanks.
Questions? So it's an elementary question. So what you showed was in those models acceleration up to velocities about 2 or 2.5 times the ion sound speed. Is that then maintained thereafter as you follow the solar wind outwards? I was under the impression that the Mach number got higher as you went out.
In this simulation here?
For example.
Or, I mean, the observation, what you have in the observation is that you have the bulk speed is reaching a given value at a few tenths of solar radii, and then the bulk speed is constant, but the temperature of the protons is slightly decreasing.
Right. So therefore the Mach number, sound Mach number increases as you go further out.
Yeah, a little bit.
But not too much.
Not too much. I think this is more or less going well with the observations.
One of you, it's typically like a Mach number of 6 to 10.
Yeah. This is stopping here
This is not.
at 50.
This doesn't have any Alpine wave physics.
No. This is just
It's the electron.
the electrons, the electrons and protons and just gravity. So the idea really is just from very simple principles. I mean, as a first order, I think that we understand the main physics. Then, of course, that the refinement is needed.
You have this picture of electron distribution
being limited by instabilities, one of which was fire hose. So what's assumed about when such bounds are derived? What's assumed about ions? And so, you know, the fire hose knows both about the electrons and about.
I think that what's assumed there is actually that that's a solution with everything Maxwellian, being Maxwellian.
I think
Both
that
the electrons.
The linear curves that people generally produce assume everything else is isotropic and change
Isotropic
one
and much
species. And a new path, obviously, that we're branching out into is, well, why don't we see what happens? Look at communication between the species. But to date, ion and electron simultaneously, we've ignored it.
Yeah, those instability thresholds assume isotropic protons.
Yeah.
The
Greg
Whistler,
has done some calculations
this is
along
probably
those
all
lines.
right for the Whistler, right? But it's certainly not all right for the fire hose, because the fire hose
Knows
doesn't
about
care,
those stuff.
right?
But this, I presume, is, this fire hose is much higher K than
Yeah.
the ion
Then
fire
the ion
hose.
fire hose it generates whistlers.
Well, what does this mean then? I mean, it's what is this fire hose?
Fire hose-like dynamics, I presume, but it might be on the same branch. But in order to affect the electrons, this must be much shorter wavelength and higher frequency than the ion. Otherwise, it would have no effect on the electrons.
But there is no. I mean, the electrons have very little inertia. There is it works. You know, you can't. There's no symmetry between ions and electrons, right? You can't quite.
Well, if
People talk about the electron fire hose, but that it's not actually clear what that is unless it's some resonant thing with the cyclotron.
I would just say
frequency
as
and
a vague caution, I don't even think I was planning on talking about this much tomorrow because Stuart's talking about instabilities, but we've been working recently on how alpha particles experience instabilities. They develop on their own. And all there is in the literature is dismissive statements about a minor ion contributes nothing to the total pressure. It can't possibly generate these instabilities. So, I mean, electrons are obviously much lighter, but in my experience so far, we've always been surprised at how easy it is for some of these instabilities to develop.
But no. Of course, the electron pressure, especially in a situation where the collisions are not very strong.
But
Can
fluctuation
be-
can be non-resonant with electrons.
Sorry.
But the fluctuation excited by an electron ferrous can be resonant with ions.
Yeah. No. Absolutely.
Yeah.
I understand.
And
Well,
not with
that-
electrons.
well,
So the
so
scales
I'm-
can be.
No, absolutely. Yeah. So that's why I'm asking, what is this threshold? It's what? It's just the regular fire hose instability based on P per I minus P per B plus P per E minus P parallel. Anyway, the ion pressure is OP plus the electron pressure is OP, so
No, no.
that gives you
No.
a fire hose, and there's only one fire hose. I mean,
Right. And this neglects the ion pressure in itself. And the growth rates are ordered by electron scales. These are calculations from a whole paper by Peter Gary.
Yes.
Yeah, and this is a
Fire-
linear, linearized Vlasov calculation. So it's not looking at the total pressure.
That's right.
Right.
It's looking at the electron anisotropy only.
And
And I will talk a little bit about this tomorrow. There are times when the solar wind acts like, a single fluid where you sum all the pressures and then you get something that physically makes sense. And there are other times where you can apply like a fluid approximation. Each of the components independently obey it. It's one of the mysterious things about this plasma.
Right. So do we know that the fluctuation? So presumably this plot could be done in this way Stuart had his plot
Yeah,
in his
yeah.
recent paper, when you could probably color it by fluctuation.
I'll show that.
Yeah. But
So
you have looked at the data?
so presumably you'll tell us that there are fluctuations at the boundary, right?
You'll see.
Not
giving it away.
So my question is, fluctuations at the boundary, are they at the electron scale or at the ion? Where are
You
they?
will see tomorrow.
Are you agreeing with what Greg has just said, that in order to affect electron fluctuations?
There should be.
I think you have to include the proton.
So there is experimental evidence that those fluctuations are on the electron scale?
No.
There is there evidence they're not?
No.
We're working on it.
It's an open topic. Yeah. And you should talk to next week when Greg Howes is here. You should talk to him because he's made, I think, significant progress in calculating the anisotropy threshold with photon. And I don't know the status of it, but a year ago he had stacks of paper.
Different topic.
Sorry?
Change subject.
Yeah.
Trapped electrons.
Yes.
The problem of trapped electrons is a very familiar one in analysis of probes and interactions of objects with plasma, as I'm sure you're aware. I mean, the wisdom in that area is that fundamentally the trapped orbits are always populated. And the basic reason is that if you have some very small level of collisions, then you populate the orbits very slowly, but you also depopulate them equally slowly. And so basically, however strong collisions are, you populate trapped orbits to the same extent. Do those kinds of arguments apply in this kind of situation, which I'm not so familiar?
Yeah. What we noticed is that, but I mean, this needs further work in order to quantify this a little bit more. But what we noticed is here is that here in these models, as you said, you can populate them, and basically what you do is you have the velocity space, you put the distribution functions. So in the region of the velocity space where you have trapped particles, you assume the continuity of Fv over these boundaries. But what we have done also is assuming just you put an ad hoc number in front of the number of electrons, and by varying that, and we compare that a little bit, but this needs further work. By varying that number and try to compare to the number of collisions that are put in the simulations, and see if the trend is the same, what we observed is that there is maybe some fundamental behavior of these solutions between the exospheric and the kinetic simulations. In other terms, if we put a full continuity, we have a solution. If we put something like 80% of the full continuity of the distribution, we have still and there is a threshold, a precise threshold at which we cannot find a solution, analytical solution for and this happens very drastically at a very precise threshold. And we have started to look this, I mean, the variation of this, but then the best, of course, is not to do that, because we know that this is just the first order. The best would be to work more on the simulations, and I think that in order to solve that, the best way would be to work more on the simulations. But we try to compare the amount of trapped particles, this amount just before the threshold, with the number of particles in the collision in the simulations. But I mean, this was at some point we stopped working on that.
All right, any more questions or comments? All right, let's have lunch.